Welcome to session 3 of feedback amplifiers. In this session, we are going to discuss 4 basic topologies. They are voltage amplifiers, current amplifiers, transconductance amplifiers, and transresistance amplifiers. So now to begin with, let us take the voltage amplifier topology. In this, Vs represents the voltage source, Rs is its series resistance, and here we have a basic voltage amplifier and the output of which is connected to the load resistor RL, across which V0 is measured. And now here we have a feedback network to feedback the part of the output voltage to the input. Here in this particular configuration, this voltage amplifier is mainly designed to amplify input voltage signal, and it provides an output voltage signal. So here input is also voltage signal, output is also a voltage signal, and therefore it can be called as a voltage controlled voltage source. Okay. And now here you can see in the diagram that the signal source is represented by Thevenin's equivalent source, that is we have this Rs in series with the Vs. Okay. Now what are the other features of this topology are this feedback network. Okay, so it will sample the output voltage. Okay, that is it will take only a fraction of the output voltage and it will feedback that to the input side. So therefore this feedback network will sample the output voltage, and we know the notation for the feedback signal we have been using XF. So therefore here the feedback signal XF is a voltage, and that feedback voltage XF, it can be mixed with the source voltage in series. So what is the source voltage here? It is Vs. Okay, so whatever the Vf is there, so that will be mixed in series with the source Vs. Okay, so therefore because of this a suitable feedback topology will be voltage mixing, voltage sampling topology. That is, these voltage amplifiers, they should have a topology in which we can get voltage mixing. The mixing will occur at the input side, and voltage sampling topology. Okay, so because of this series connection where at the input side and also there is a parallel or shunt connection at the output, this particular topology is also known as series shunt feedback. Here in the diagram you can see that. Okay, so what we have, series mixing at the input side, but there is a shunt connection or parallel connection at the output side. Okay, so because of this connection, this topology is also known as series shunt feedback. So next we have current amplifiers. So in case of this particular current amplifiers, okay, the input is also current as well as the output signal is also current only. Okay, so therefore here at the input side you can observe the signal source. Okay, so it is represented by Norton's equivalent circuit. Okay, so I am talking about this particular source, Is and Rs in parallel with the current source Is. Okay, so here the output is also current only, that is I0. In the diagram you can see I0. Okay, in this topology. So therefore the input is also current as well as the output is also current in this. So therefore here obviously the feedback network, whatever is employed in these current amplifier circuits, it should sample output current. In the previous topology, the feedback used to sample output voltage, but here in this topology or here in this kind of current amplifiers, okay, the output current will be sampled. Okay. And also as the feedback signal is current, okay, so it will be mixed in shunt or in parallel with the source current. So this you can see in the diagram that at the output we have the series connection, but at the input, okay, so the feedback current will be mixed in parallel. Okay. So therefore this particular topology is also known as current mixing and current sampling feedback topology. So this current mixing, this refers to what? The mixing of feedback with the source at the input side. This current sampling, it refers to the action that is being taken at the output side. So current is sampled and current is mixed in parallel. Okay, so But what is the type of connection? So there is a parallel or shunt connection at the input. You can see in the diagram, parallel or shunt connection. So this is a parallel connection, but there is a series connection at the output side. Okay. So therefore now this particular topology is identified by a particular name known as shunt series feedback. So here the word shunt, it refers to the input side. Series refers to the connection at the output side. Okay. So because of this connection pattern, this topology is also known as what? Shunt series feedback. Similarly, we have another topology, that is in case of transconductance amplifier. Okay. So in transconductance amplifier, you just observe the block diagram. So now we can identify that both at input and output there is a series connection only. But here we have represented at the input it is Vf, but at the output it is I0. So that is, in previous two topologies, inputs and outputs were both either voltage or current. Okay, that's why they were either voltage amplifier or current amplifier circuits. But here in transconductance amplifier, you can see that the mixing is now different. Okay, so I0 is seems to be sampled here. I0 is sampled and it is mixed with the voltage at the input. Okay, so therefore let us know something about this transconductance amplifier. So input signal is a voltage. Okay, so that is clear from this. Input signal is a voltage, but here the output signal is a current. So that's why I0 we have mentioned here. Okay, so therefore now what is the type of mixing that is done? Voltage is mixed, therefore current is sampled. That's why this feedback topology, in this feedback topology what we find? Voltage mixing and current sampling. So mixing is done, it is at the input side. Current sampling refers to the action at the output side. So therefore the transconductance amplifier topology has voltage mixing and current sampling. Transconductance it is. And also from the connection type, we can see that both at the input and output we have series and series connection. So therefore obviously we can now identify this particular topology as series feedback. Okay, so now just you can have a little bit comparison with the voltage amplifiers also. So as in case of the voltage feedback amplifier, so the series connection at the input, okay, so results in an increased input resistance. So this is one of the features in case of transconductance amplifier. So it has increased resistance at the input, and the sampling of the output current at the output. Okay, so it results in an increased output resistance. Okay, so therefore increased input and output resistance are the desirable properties with respect to these transconductance amplifiers, and that is achieved through this topology. Similarly, moving back to the next kind of configuration, we have trans resistance amplifier. So now in trans resistance amplifier, now you can just observe from the diagram what we understand here is the mixing is current as well as sampling is also current only in this. Okay, so here just a minute, sampling is a voltage. Okay, so V0 is being sampled. So therefore in this trans resistance amplifier, input signal is current, but the output signal is a voltage. Okay, so V0 is being sampled. So therefore the appropriate type of for feedback topology that is good for this trans resistance amplifier is a current mixing and voltage sampling. Why? Because at the input current is being mixed with the input source Is, but at the output what we have, V0 output voltage is being mixed. And also just by observing the connection, so both at the input and output what we have is the parallel or the shunt connections. So therefore now this topology is identified by name shunt feedback. Okay, so indicating that both at the input and output we have the parallel connection. Okay. So now the shunt connection at the input, it causes the input resistance to reduce, and at the same time the shunt connection at the output is going to stabilize the output voltage, and thereby it causes the output resistance to be reduced. Okay, so therefore here the trans resistance amplifier, so it has the properties of low input and low output resistances. So now these are the some of the features associated with the four basic topologies. Now this table presents the summary of all the feedback topologies. Okay, so first one, voltage amplifier. What is the type of feedback we have? Voltage mixing, voltage sampling. Okay, and this is also known by the name series shunt feedback. Okay, so therefore feedback type represents what? So how the mixing is done at the input and how the sampling, which quantity is sampled, which quantity is mixed. Okay, and here the feedback name is this indicates whether the sampling and mixing is done in a series pattern or in a shunt or parallel pattern. Okay, so with respect to voltage amplifiers, we have voltage mixing, voltage sampling. So therefore this topology is also known as series shunt feedback. Similarly, with respect to current amplifiers, so here current is mixing, current is sampling. So therefore this is also known as shunt series feedback. Okay. So whereas in transconductance amplifier, so here we have the opposite quantities at the input and output. So here the feedback type will be voltage mixing and current sampling. Okay, so here the type of connection that we find is a series feedback. Okay, then the last one, trans resistance amplifier. So in this, current mixing, voltage sampling is the type of feedback we have. So because of this connection, this topology is also known as shunt feedback. Okay, so therefore this is what is the summary of the four basic topologies with respect to feedback amplifiers. Thank you.